Color measurement instruments are critical when it comes to defining pass or fail color criteria for your physical samples, and these instruments are typically either colorimeters or spectrophotometers. While colorimeters can determine a color's location in color space using LAB or LCH metrics, that alone is not always sufficient data. In many industries, they may fail to identify crucial color matching errors. Let's take a look. Here we have a Pantone D50 lighting indicator. Under daylight, we can visually see that the color on the top half and the bottom half closely match. If we measure and plot both halves in C-Lab, the two colors appear identical and the numerical color difference is very small. Now if we change the lighting to a typical fluorescent light, the top half now appears green and has changed location in C-Lab color space. So what happened? These two samples are considered metameric matches, and C-Lab values by nature are defined under very specific viewing conditions. This is where spectrophotometers can help. Every physical sample we measure has its own reflectance, or the amount of light it reflects. Think of it like a fingerprint that is unique to that sample. A spectrophotometer measures a sample's reflected light to capture its fingerprint and determine the amount of light reflected from different portions of the visible spectrum. This is typically achieved within an instrument using a spinning filter wheel of specially designed colors or a diffraction grating. The resulting measurement is the sample's reflectance curve with a varying wavelength from around 400 to 700 nanometers. From this, we can compare the curves of two samples to see if they are a match. So back to our metameric issue. Here we can see the spectral measurements of the top and bottom of the lighting indicator. They are definitely different. The color of the indicator can shift depending on where the wavelengths of the physical sample align with the spectral power distribution of the light source. So guess what happens when we match the two spectral curves? We get a match under every lighting condition. Now to make things slightly more complex, if all samples were flat, opaque, or the same thickness, one instrument would work for all industries. However, in reality, other types of materials must be measured, such as curved surfaces, transparent objects, and textured objects. For this reason, different instrument geometries exist. Let's take a look at the three most common types to wrap things up. One of the most common is the 045 or 45-0. The 45-0 measurement geometry emits light at 45 degrees to the sample surface and measures light reflected at a fixed angle to the sample, 0 degrees. This geometry excludes gloss to most closely replicate how the human eye sees color and is commonly used for measuring color on flat, smooth, or matte surfaces. Next are spherical instruments, which captures light reflected from all angles of a sample. This measurement can include or exclude the surface appearance of your sample. These devices are commonly used for measuring color that has been applied to textured surfaces such as textiles, carpets, and plastics, as well as glossy or mirror-like surfaces, including foil printing. Finally, we have multi-angle instruments, which view the color of a sample as if it's being rotated back and forth, just as you would twist a sample to see the color at various angles. Today's multi-angle instruments are typically used for specialty coated pigments and special effect colors with additives such as nail polish and automotive coatings. Spectrophotometers are used in every industry that requires accurate color. From packaging to textiles and even plastic parts, these devices help ensure that the color being produced matches the color that was originally specified. When choosing a spectrophotometer, it's important to find one that will meet all your needs based on what you're measuring.